Okay, I think we'll go ahead and get started. Pleasure to welcome you back again this week for another in our Breakthrough Seminar Series. I'd like to also welcome our simulcast universities, University of Manitoba, University of Calgary, University of Alberta, and one or two of the UBC schools, depending on who's tuning in today. I'd also like to thank Howard Weeder and his CERC and the Global Institute for Water Security for underwriting this seminar series and giving us the opportunity to bring Keith Beven here today from Lancaster University. Keith is University Distinguished Professor of Hydrology at Lancaster University and also at Uppsala University in Sweden, where he has a partial appointment. And Keith really, I think, is the greatest thought leader in hydrology probably since Robert Horton. I remember putting together an AGU Horton Medal nomination for Keith, and one of the letter writers was George Hornberger from the University of Virginia. And in George's letter, he wrote, for a beginning PhD student, no one could do any better than to go back and look at all of Keith's papers in terms of really understanding the evolution of the field over the last 40 years, where Keith has played really quite a significant role. You've seen the bio in the today's handout. In addition to his 350-odd papers, some of his textbooks have been very influential. The rainfall runoff modeling, the primer, has really, I think, influenced the field in terms of driving home many of the issues of uncertainty, of parameter identifiability. His book that he'll be kind of lecturing from in tomorrow's all-day seminar, Environmental Modeling an Uncertain Future, has also helped to galvanize, I think, the environmental modeling community around really recognizing uncertainty in our estimations. Obviously, Keith has received a number of awards from a number of organizations. I mentioned the Horton Medal from the AGU, also the Langbein Award from AGU. He's recipient of the Dalton Medal from the European Geophysical Union and the IHS WMO UNESCO International Hydrology Prize. I think what's most remarkable about Keith is he's really a selfless giver of his time, particularly to PhD students and postdocs. He does an annual short course at Uppsala each year and comes to Aberdeen each August to teach a module in a catchment science summer school conducted there. So it's really a pleasure to have Keith with us in Saskatoon, and I'll turn it over to him for today's seminar.
Thank you, Jeff, for those kind words. I'm not sure it is actually a good recommendation that all PhD students should read all of my papers. It might take them 3 years or so to actually do that. But I'm going to talk largely today about uncertainty estimation. It's something I've been concerned with ever since my PhD thesis, when I actually did a modeling exercise that didn't work out too well, and therefore I wanted to understand why. And basically I've been trying to do so ever since and find ways of expressing some of the uncertainties that we have to deal with in environmental modeling, and trying to understand those in a way that will lead us to do better science. So that's what I want to talk to you about today. I'll start with a summary of what I want to get across to you so that I can plant these ideas in your head while I'm talking. Hydrology is an inexact science. The fact that it may be impossible to separate out sources of error from series of modeled residuals. The fact that there's lots of uncertainty about uncertainty estimation. And there's a good reason for that, because there's no right answer. The types of uncertainties we have to deal with mean that it's very difficult to represent the different sources of uncertainty in rigorous ways. We're forced back usually to some sort of subjectivity to do that. And that there are dangers in trying to represent all uncertainties as if they were random or arbitrary in nature. I've been working on an approach to trying to structure approaches to uncertainty estimation called GLUE, the Generalized Likelihood Uncertainty Estimation, work that I started in about 1980 and are still learning about. But that's based on ideas of the fact that when we look at an environmental system, there may be many different models that give us acceptable results in terms of trying to predict the nature of that system. And that may be both different parameter sets within a model structure, and it may be possible competing model structures as well. And we need ways of trying to evaluate competing models with respect to the data that we've got. I'll talk a little about a limits of acceptability approach that we've been using recently as an alternative to statistical testing of models as hypotheses, and the need to give attention to agreement about assumptions when we try and communicate to uncertainty to the real decision makers, which is why we may be doing some of this modeling in the first place. Why should we be interested in uncertainty? Science has sort of muddled along in this area for a long time without worrying about it too much. And I think there are a number of reasons, and the first one is the fact that our models are wrong. And we know that they're wrong. Of course, going back to George Box's, the statistician's maxim that all models are wrong but some might be useful, we want to try and differentiate between what might be useful from those that we should be very worried about making predictions with. So trying to do that evaluation is quite important. But that evaluation is always going to be conditional on what types of data we've got, the quality of the data with which we're looking at forcing models as input data and boundary condition data, and evaluating models in terms of observables that we might compare with things that are being predicted. We have a situation in many environmental systems where our models, our equations contain parameter values, and we like to think that those parameter values have some physical significance, but the things we can actually go out and measure in order to try and determine values for those parameter values might be quite different from the values that are required to make a model work or not. Commensurability issues that might have to do with scale of the measurement relative to the scale of predictions that we're using, and so on. And therefore, we're generally forced into some sort of calibration exercise to try and see how well a model can fit a certain data set. But then the observations with which we can compare a model are also wrong and are known to be wrong. In some cases more than others. As a hydrologist, I'm often interested in the peak discharges for flood forecasting purposes or flood design purposes. But the errors in flood discharges can be horrendous because we're very often extrapolating up to levels that haven't been seen before under conditions in which it's extremely difficult to make an actual measurement of a field discharge. I think the result of all that is this idea that it may be very difficult to differentiate between competing model structures as hypotheses about how things are working. And this is what I've labeled the equifinality thesis. Equifinality to give an indication that many models might give you acceptable results. And I wrote a paper explaining that thesis in Journal of Hydrology in 2006. But it builds upon work that's much older. Equifinality was first used in this context by Ludwig van Bertalanffy in his book on general systems theory that was published back in 1968. So these are not necessarily new issues that I'm addressing here. They've been around for some time. The question is whether we can use them in finding better ways of doing the science. If I go back to the 60s and 70s, I started my research career in about 71, I think. As I said, uncertainty estimation is not new. There was stuff going on at the time in the 60s and 70s. As soon as digital computers were available, people were generating stochastic models and uncertainty estimations and so on and so forth. And I've just labeled some of them there in terms of stochastic order resources models, Meyer and Fielding, Yevdovich and others, realizations of extremes, fluff frequency analysis, Jim Wallace's work, John Hoskins' work. There was work being done already on the effects of heterogeneity on hill slope responses within modeling frameworks by Al Fries, Roger Smith and Hebert, Bayesian analyses for updating. And in fact, the first stochastic hydrological catchment model that I know was written by somebody called J. Bagley. He used a Markov chain, transistor probability type of approach for various stores within the catchment system, and it was a Stanford PhD thesis at just about the same time as the first deterministic model was coming out of Stanford, the Stanford watershed model, where the equivalent publication, the published thesis was, I think, for the Stanford model 1962. So these are directly analogous in terms of time. Mostly these are rather deterministic outputs from stochastic realizations without worrying too much about evaluations against data. And I think things get much more interesting when we start to concentrate on some of the issues about how do you evaluate your models, how do you condition your model outputs when you've got some data. So that's what I'm going to concentrate on. But I want you to remember that we may be doing this for a purpose. Okay? It's not just doing the science for the science's sake. And as an example here, I use, in Europe, we have a European directive called the Water Framework Directive that is requiring all countries in the European Union to manage their water bodies to good ecological and chemical status for sustainable use. There's some flexibility in what good ecological and chemical status means, and there's some issues about defining what sustainable use means, but the principles are established in there. And there's a requirement of river basin management plans and program of measures for every water body. There's a requirement for integrated and sustainable management across whole catchments as opposed to individual places, with special arrangements for habitats, drinking water areas, bathing water, and so on. It raises all sorts of questions in terms of real management issues and how you prioritize the spend of money to try and achieve good ecological and chemical status. What is good status, particularly on the ecological side? How do you define sustainable use? And all of these essentially require some predictions of what's going to happen in the future, particularly if you introduce some improvement measures. How are you going to define your new capital expenditure for those improvements in an integrated way? And that's where modeling for decision making is an example of how we might look at things. You can probably just about see the grey there. I've blanked out some of these stages in the modelling process to show what we're going to concentrate on in this talk. But I also want to illustrate that there's an important levels of approximation in going from what our qualitative understanding is about how a system is working, which only needs to be up in your head. It only needs to be ideas, and therefore it can be as complicated as you want it to be. It reflects all of your understanding of the complexities of spatial heterogeneities and time non-stationarities in the types of systems that we're looking in. But that's not very useful for making quantitative predictions for decision making. We therefore need to define some equations, what I call here the conceptual model, and then implement those as code to get some predictions out. And it's really important, the fact that we're making increasing approximations in going from that very complicated perceptual model down to something that's going to produce quantitative predictions for us. The bit we're going to concentrate here, having recognized that, is that we're going to require some parameters in those models, the calibration process, and hopefully getting down towards some validation process as well. And because of that approximation and because of the uncertainties in our forcing data, that's why we should be worrying about uncertainty estimation within the modeling process. And in doing so, hydrology is one of the inexact sciences. If we look at the inputs, the outputs, the storages, the uncertain flows that we might have through bedrock, the interaction with land management effects that we don't understand too well, and so on and so forth, there's lots of inexactitude here. But I use that phrase partly because in 2000-2001, I was fortunate to be invited to have a sabbatical in the Catholic University in Leuven as a visiting professor that was funded by the Franke Foundation. And the Franke Foundation offers 3 visiting chairs every year. one in medicine, one in humanities, and one in the exact sciences. And I didn't really understand why I qualified under any of those. Certainly not under humanity, certainly not under medicine, and certainly not under the exact sciences. And I had dinner with the director of the Franke Foundation who offers these visiting chairs, and suggested to him that they really needed a fourth. And that was in the inexact sciences, because they're so much more difficult than the exact sciences. And yet, in all of our environmental problems, we're having to deal with these inexactitudes or uncertainties in all of those processes. And if we start to make a list of the types of errors that we have and why they're important, we've already mentioned errors in the input and out and boundary condition data. Errors in the model structure might be important. We don't have proper, really realistic representations of the processes. Within the model structure, we're going to have errors in estimating the parameters we require to get good results. There may be commensurability issues between things that have a name that in our physical theory and things that have the same name in the model but mean different things, either because of time scales or space scales or other issues that are involved. We're going to have errors in the observations, which we use to calibrate the model. We're going to have errors of omission, things we've left out. And sometimes we know that we've left them out because we don't really know how to deal with them. Preferential flows in soils is a good example that is often left out of hydrological models. And we also have, in Donald Rumsfeld's phrase, the unknown unknowns, the things that may yet surprise us. Now, out of that list, in fact, this is the only one we don't have to worry about, because we don't know about them yet. But as soon as a surprise happens, and we realize that something is not quite right, then we have to start, they become known unknowns, and we have to start to worry about them. Now, if we think about that in terms of really the most basic equation in hydrology, the water balance equation, and we think about how far we can test that as a model by measurement, very often, of course, we don't actually test it. We just assume that it holds. We measure our discharges, we measure our rainfalls, we integrate the change in storage over a water year or something like that and assume that it's negligible, and then we lump all of the errors into the evapotranspiration component. That's not really a test. In fact, by measurement, since we have rather poor measurements often of discharges, we have often rather poor measurements of the overall rainfall inputs to a catchment area, we very often have poor measurements of evapotranspiration and change of storage. It's very difficult to verify that as a hypothesis by measurement. Something that Nancy Cartwright, the philosopher, calls something that is more of a capacity of the system than something that can verify. In fact, her example is the second law of thermodynamics, which, of course, is widely applied as a good physical principle, but in most practical applications is very difficult to verify by measurement because of the uncertainty in the measurements. And of course, there may be some things that we've actually left out of that equation already because we don't know enough about them in terms of transfers in the groundwater, underflow through your gauging system or whatever. So there's many sources of uncertainty, and as I said earlier, there's no right answer. And this is one of the reasons why there's so much uncertainty about uncertainty estimation. It leaves lots of scope for different types of interpretation of how to deal with all these different types of uncertainty. And one that's particularly difficult to address is really the model structural error. It's not easily separated, as we'll see, from other sources of error without making rather strong and difficult to justify assumptions about your sources of error. So we often make an assessment, particularly if we're working within a statistical framework, of estimating the certainty as if the model was correct. And yet we know that our models are wrong and are known to be wrong. But one of the results of that is that there's lots of uncertainty estimation methods. What I'll do today is largely concentrate between the contrast between statistical estimation or statistical inference theory and its approach to assessing likelihoods, and my generalized likelihood uncertainty estimation theory, and show some different aspects of those. In the form of statistical approach, you essentially use some assumptions about the nature of the errors to formulate a likelihood. And you evaluate different model structures, different parameter sets within model structures in terms of that likelihood. You may sometimes use some transformation of the errors to get them into the right sort of statistical framework, but essentially you're assuming that the errors are additive and fundamentally at the end random or aleatory in nature. And you also make the conditionality on the model being assumed correct. That leads you to essentially assuming that every residual that you can evaluate, some difference between an observed and predicted variable, contributes something towards the shaping of that likelihood function towards the shaping of the posterior probability distribution for your outputs. And I think there's a problem with that, because in many of our sources of error, we're not really dealing with random variability. We're actually dealing with much more of a lack of knowledge about what's actually going on. And that has characteristics that aren't necessarily random. They may be structured in some way. Yes, if it's consistently structured, you can take account of that in a statistical error model. But they may also be rather arbitrary in nature and non-stationary in nature, in which case it's much more difficult to take account in a statistical error model. If we look at those different types of error and think about whether they have aleatory components or epistemic components, or even the D here, which I thought I'd introduced by now, but D stands for disinformation being fed into the modeling process. Then we can see that our input and boundary condition data might have all three. The model structure probably only has epistemic or disinformation in it if our model representations are wrong. And if we go all the way down to the known unknowns, that's going to be probably disinformative in terms of the modeling process until we know something about the fact that we've missed something out, and in which case it may become epistemic and disinformative. And we can think about each of these terms as well in terms of whether they should be random or epistemic, or might actually bring disinformation into the process. So in terms of statistical estimation, basically we often try to find a maximum likelihood model or some optimal model and treat that as if it was a true model, and then look at the residual structures that are associated with that maximum likelihood model and try to come up with a representation of that structure in terms of a statistical error model. And the nature of that error model then defines some likelihood function that we can derive by statistical theory. Then the sum of the model and the error distribution can be used to estimate the likelihood or probability of predicting a new observation conditional on that model. And this derives from the development of statistical theory, looking at fitting of distributions through likelihood estimation, treating the variations, the residuals, as if it was a form of additive measurement error. How that's done most commonly now is within a Bayesian framework. Bayes equation comes from the Reverend Thomas Bayes, who was a gentleman priest in the 18th century in England. And after he died, in his papers was found a sort of scientific paper called the Essay Towards Solving a Problem in the Doctrine of Chances. And this was presented to the Royal Society of London by one of his friends in 1763 and published by the Royal Society. It was developed independently in France by Laplace in a discrete form in 1816. And basically, Bayes suggested that if you wanted to get some estimate of the posterior likelihood of a hypothesis given some evidence, you would have some prior beliefs in what the probability of that hypothesis might be, and then you might want to try and estimate some estimate of the likelihood of the evidence given that hypothesis. And if you divided all that by some scaling constant, then you could get a posterior estimate of the probability of your belief in that hypothesis. He actually expressed it all in terms not of probability, but of odds of representing a hypothesis. That's now often used in the form that we try to estimate the probability of predicting a new observation, so with the additional error model, conditional on assuming that a model or set of models represents a correct representation of the system based on some prior probability for each of the models we want to try, and then the likelihood of reproducing our calibration data or observations, comparing the residuals between observed and modeled variables. The model evaluation is normally based on residuals in space and time. And so we just calculate residual based on some observation subtracted from the model prediction, where the model prediction may depend on some parameter sets, theta, and some inputs, the capital I as a vector of inputs. It's important to recognize that that error may be made up of multiple sources of terms. And I've split it down here into a modeling component, so a model structural error component, where our parameters may have themselves some error associated with them, our inputs may have some error associated with them, and that will be variable in space and time. A commensurability error component that may depend on our space and time steps or discretizations. An error associated with the observation that might vary in x and time, in space and time, and probably at the end there's some purely random component that we can't reduce anymore. If we follow the through assumptions about the nature of the errors within a statistical framework, for example, assuming that our residuals have the very simplest structure, which might be zero mean, they're independent in time, and Gauss distributed, then we end up with a likelihood function that looks like this, where we have our error residual variance here, squared, in this term, and over in that term, the sum of the residuals over there, and we have this minus n over 2 term, raising the residual variance essentially to a power of n over 2, where n is the number of residuals we have either in space or time. Now, in hydrology, we often have quite long time series with which we're fitting data. Often the residuals are autocorrelated in time, which can reduce the effect of that, raising the residual variance to a power a little. But the dominant term here is very often this term here of taking our residual variance and raising it to the power of n over 2. Because if n is large, if we have actually a large number of residuals, by looking at time steps over a considerable time series, then we may be raising that, let's say if we have 1,000 time steps, to a power of 500. And that's a very, very strong conditioning process. If we think about our likelihood as a surface in dimensions of the model space, we're actually stretching that surface out dramatically by making these statistical assumptions. And if I give you an example here of a likelihood ratio, so the ratio of the likelihood for two model realizations updated after 1, 2, 3, 4, 5, 6, so on, years of data. And I've chosen two models that initially have very similar error variance, so the ratio is close to 1. But you can see that that changes over time. As I add more data, the changes over time. Initially, one model becomes much better than the other, and then there's some recovery for a different time period when the second model becomes better again. Now, the important... I thought I had to bring out this axis here. You may not be able to see this axis very well, particularly from the back there. This is 10 to the 0, 1. Okay, so this is saying that that likelihood ratio starts off close to 1 because those are two models of very similar performance in the first year. This is 10 to the minus 20. And this is 10 to the minus 40. Okay? And this actually was a model, an evaluation of likelihood that includes the effect of autocorrelation in the residuals. The stretching would actually be even worse if you left out that autocorrelation. You're saying that these two models that initially seemed to have very similar performance are now being ranked in terms of likelihood with differences of 10 to the minus 40. One apparently is so much better than the other. And it comes directly from making the statistical assumptions that lead to that likelihood function. This is why the statisticians always work in log likelihood and not in likelihood, because if you work to 10 to the minus 40s and things, you start to get rounding error issues about evaluation of models. Those who only work in log likelihood, of course, will not realize that you've got this stretching because your log values are only 20 and 40 and so on. Now that worries me, because if we think of that idea of the likelihood surface as a response surface in some model space, the functioning of a model can always be represented in terms of what's happening in terms of variables or likelihoods within that model space, where your dimensions may have maybe the parameters of the model, or may actually be different model structures as well. The response could be a particular variable that's being output from the model, or it could be one of these likelihoods. But in terms of making an assessment of how well a model is performing, if you go through the statistical likelihood theory, you can see from that previous diagram that the effect is to really stretch that surface out until one model appears, or a small number of models will appear much more likely than others. And given that we're not dealing with random uncertainties, we're dealing with epistemic or knowledge uncertainties, that seems a dangerous type of approach to me. It means that we might be generating overconfidence in our inference about which models are good and which models are bad. This idea of thinking in terms of response surface and the uncertainties associated with that, I think, is quite useful, because if we had enough computer time, of course, we could run so many models that we could evaluate all the responses everywhere in that surface. That's still somewhat difficult with climate models, but it is possible with some of the simpler models that we might use in hydrology and water quality. I think our record is 2 billion runs for one particular model, of which we accepted 216 as being having the right sort of acceptable behavior. The idea, though, is that in principle everything is known within that space. So where does the uncertainty come from? The uncertainty comes from trying to map your bit of the landscape that you're interested in into that model space. We can evaluate everything in the model space. What we don't know is how well our landscape maps into that space. And in particular, if we look at that mapping as a sort of, we can't do that with any certainty, so we're going to end up with our landscape being represented by clouds of models within that space. We can think about those as multiple working hypotheses about how our system is actually operating. And then there's the possibility that you might be able to test those models as hypotheses as to how well they're reproducing the behavior of the system. And that you might be able to reject some as not being the right type of behavior in terms of reproducing the system. And this is basically the essence of the glue methodology. The issue is, what should those tests look like for different types of problem? But if we look at the uncertainty as that likelihood surface in the model space, we can sort of actually use quite relaxed definitions of likelihood in terms of what we require. One thing that we require is that as our models get better, we should give them a higher likelihood. Another thing that we require is that if we've got reason to reject a model, we should give it a likelihood of 0. Statistical estimation theory tends not to do that. It tends to give very, very, very low likelihoods, but not actually to reject unless you impose some additional rejection criteria. So the likelihood then is actually acting as a scaling of your belief in how useful a particular model might be in prediction, rather than as a probability. As I say, this is the basis of the GLUE methodology. It's based on rejection of the idea that you may be able to find the best model, that you may be able to optimize your model structure, because it appears that optimization or maximum likelihood will not be robust to either calibration period, performance measures, likelihood structure. And so that's the essence of the equifinality idea. It suggests that it's not sufficient to deal with errors from some optimal model as random, that you can still assess some likelihood or as a measure of belief in a particular model, structure and parameter set. You can reject the models that you don't consider to be adequate. And if you evaluate all your models in the same way, you can actually incorporate different model structures into this, as well as different parameter sets. And this came out really of starting Monte Carlo experiments, actually while I was still working at the University of Virginia back in 1980, just running different model realizations and producing plots like these, so-called Dotty plots, because they're made up of lots of dots, so it seems a reasonable name. And each one of those dots is one run of the model. And what's on the x-axis here is the range of a particular parameter that's been sampled. What's on the y-axis is how well that model is doing in some sort of likelihood measure. In this case, it's a sort of modeling efficiency, so 1 represents a perfect model, and we're getting up here to about 0.9. And each model run is made with a random selection of each of the parameters across the range that you see there. In this case, uniform distributions have been used for the prior distributions of parameters, but other distributions could be used. And it's fairly typical of the type. This is actually for a rainfall runoff model, but it's fairly typical for the types of behavior that we see. 1 or 2 parameters show some shaping in terms of the outputs that you get. These are actually effectively projections of the points that you've sampled in that model space, the likelihood surface in that model space, projected down onto one parameter axis. So although they don't show the complexities of the structure of that surface, they do show where your good models are, in terms of the best ones being up at the top. But you can see the very best one is actually separated out from this shaping. There's some out here that are doing quite well, and also out here that are doing pretty well, and the best one is here, that's independent of the shaping that you get. And the other thing you can see is that for many of the parameters, there are good fits all the way across the range that you've tried, and relatively poor fits all the way across the range that you've tried as well, so that any particular value might produce a good fit or a bad fit depending on the values of the other parameters. It's a parameter set that gives you a good fit or a bad fit to your observations. Now, if we take a sample of the best models, the ones that we're going to accept as possibly being useful as predictors into the future, then you can use that as an ensemble to produce probabilities for the outputs as predicted by those model structures. And we've done this for that same rainfall runoff case. We've got a 5 and 95% limit here for the predictions, and for this particular application, the model's actually doing quite well, except actually for the bit I'm most interested in. If I'm interested in flood peaks, you can see that this flood peak has an excursion outside of what my model can actually predict, or my sample of models that have been deemed acceptable can actually predict. That could be, of course, just because of the forcing data that I'm giving the model. This rainfall here was an underestimate from the particular sample of rain gauges that I have of what actually went into the structure. It could be that there's some deficiencies in my model structure in representing the processes in the catchment. It's very difficult to separate out those those different effects. Glue's been applied to a whole load of different application areas now. We started with rainfall runoff modeling, but other people have picked it up, for example, in using water treatment processes and other types of forest fires and other types of applications. And this actually has been accepted this week. There's now a Glue 20 years on paper that I heard this week has been accepted, will be published in Hydrological Processes. And there's an electronic attachment to that that actually gives references to applications in different application areas. So you may want to look out for that to become available. Glue has, however, been controversial. And I wanted to say a little bit about the Glue controversy. And you can look up a sequence of papers in the Journal of Hydrology, starting with Beven and Dotty in 2006, with a response by us in 2008, and various hydrological processes commentaries, starting with one called On Undermining the Science, because one of my esteemed colleagues at an EGU meeting once suggested that by making so much of all this uncertainty stuff, I was actually undermining hydrological science. And there's a sequence of commentaries going to one where I tried to summarize the discussion on doing better hydrological science in 2008. The issue is essentially as to how far you can treat your uncertainties in a probabilistic framework and how far you have to worry about them as knowledge uncertainties, epistemic uncertainties, and so on. And the Beven and Dotty paper suggested that there was a basic statistical principle that should be followed, which was that you should be coherent in the sense that every time you got a residual, it added some information to the conditioning process, and that's why you can combine your residuals in a way that leads to that very strong conditioning in that Gaussian likelihood function. My point is that really only applies if those errors are really random. Biased or autocorrelated errors are known to lead to biased parameter estimates. And if we don't get the structure right, then our inference is going to be overconfident. And that's quite clear from that very strong conditioning I showed you in that likelihood ratio plot. And that's going to be worse if the errors are epistemic. And in our 2008 response, we actually showed that even if you, for the hypothetical example that Beven and Dotty had used, even if you had small departures from their assumptions, it actually leaded you to bias inference within the statistical framework. So if your errors are epistemic, and I'm sure that in most environmental modeling cases they are largely dominated by lack of knowledge or even being disinformative, then we should be very wary about making that strong shaping of any form of likelihood estimation. So let's just look at the differences between the Bayes approach and Glue. So in formal Bayes, your uncertainty has to be expressed as probability of predicting an observational, conditional on the model being acceptable. And there's still an underlying idea of trying to find the model in that type of approach. You're making an assumption that some sort of suitable formal likelihood, however complex, can be found to represent the total error, or in a hierarchical approach, individual error sources, and you can always find such a structure and assume that it has properties that you can parameterize, essentially. That the data is always coherent, and the information content of new data can be evaluated by looking at change in some shaping factors, some discrepancy measure in the posterior distribution. Your prediction bounds should then bracket the 90 to 95% level, or whatever you want to choose for for the observations that you've got, both in the calibration and in prediction. And if you actually misuse that, and there's lots of examples in the hydrological literature that I know of where people have actually misused likelihoods by not using a structure, not verifying a structure against the actual nature of the residuals, that should be considered as poor practice. On the other hand, we have glue, where we accept the idea of equifinality in the face of all the different sources of error. But the result is that you don't end up with uncertainties that express a true probability of predicting an observation conditional on your models. You end up with an expression of your belief in a set of predictions from your ensemble of models that you think will be useful in prediction. And in that case, the prediction limits may not actually bracket the observations to 90 or 95% or whatever other quantile you want to use. But that can be useful. It can actually tell you when there's something wrong in your representation or in your data that might lead you to improve the science. There are some cases where there's absolutely no way, whatever model you try, it can bracket the observational data that you've got. And that can be useful as a structure. You can actually look at formal likelihoods as a special case within this framework where you're prepared to make the strong statistical assumptions necessary. And I make the point that you can also have poor practice here in terms of how you interpret those likelihood weights. The most important characteristics of glue, I think, are that you can look at it as a rejectionist type of framework in doing testing of models as hypotheses. So you would want to reject those models that do not give you good predictions of your observations in some sense. That leaves open the possibility, of course, of rejecting all of your models that you try. And I've published a number of papers now in which I've managed to reject all of my models that have been tried and get that through the referees. That is a good thing, okay, because it means you've got to do better. Fortunately, the referees haven't come back and said, okay, you've rejected all of your models, what are you going to do to make it better? But that's the obvious next step that you've got to consider if you're forced into that situation. Rejection is then a form of hypothesis testing, thinking about our models as multiple working hypotheses about representing how the system is functioning. There's an important point there that we don't really want to make the errors analogous with statistical inference of rejecting a good model just because we've got errors in the calibration data, or accepting a poor model just because we've got errors in the calibration data. So we have to be careful about rejection. We have to try and take account of some of the sources of error in doing that hypothesis testing. We don't want to reject the very simplest model of the water balance just because we might have poor estimates of rainfall, for example. And we can't check that against the measurements of the other terms. Rejecting a good model just because you've got poor input data or evaluation data, of course, is much more significant than accepting a false model, because you would hope that as you gather more data and test your model a little bit further, eventually you might see that your false model is actually false. Whereas if you've already rejected your good model, you might never get it back again. The retention of multiple behavioral models is analogous to having multiple working hypotheses. So this is a way of doing science, okay, within this really difficult, uncertain type of process system representation. And it's possible that we can come up with some testable hypotheses that might actually allow us to constrain our set of models, feasible models, further. It does require that we can actually collect the data to make that test, and that we have some suitable criterion of rejection, that things aren't so uncertain that's not going to be a strong test. So that would allow some additional conditioning of our model space. So this is what we're doing at the moment. One first step is to actually look at your data very much more carefully than we have done in the past and see where there are inconsistencies in that data before we start any model evaluations at all. And I may have an example of that later. Certainly for those of you who are going to be doing the workshop, we'll discuss this much more in the workshop tomorrow. And then following on from my manifesto paper is the idea of setting up limits of acceptability for each observation with which we're going to compare our model based on what we know about the data prior to making any model runs. And then that will be a suitably independent source of model evaluation because it's not dependent on any particular model structure. Having got those limits of acceptability for each model run, we can evaluate the performance against those. And, oh, that should be number 4. And we can also actually look at the sequences of residuals that come out to see if there's any residual structure that we can learn from or use in terms of representing our additional error in our predictions into the future. One of the nice things about this is that it does allow to some extent for the fact that you might have changing biases in the way in which you can make model predictions. And I'm representing that here by saying, okay, let's take an observation. Let's specify some limits of acceptability around that observation, and let's look at where my model predicts over multiple realizations to see how many of my models fall within those limits of acceptability. And here's a case where the histogram here represents the histogram of model predictions, but none of them can bracket, none of the models I've tried can actually bracket that observation. It's biased towards the upper end in that case. In another time step or another spatial point, it might be biased to the lower end. In other cases, it might actually bracket the observation. But we're not, we're trying to allow here for non-stationarity in the types of performance that we might get out of the model predictions. We can actually look at those biases and changes by using a normalized scale for the model predictions. And here I've got 2 models, one the solid line, one the dot dash line, plotted as outputs against time, but on a scale where it's scaled by my limits of acceptability. So 0 means that you're reproducing the observation. 1 means you're on the upper or above, at or above the upper limit of acceptability for that observation, and -1 means you're at the lower limit of the observation. You can see that both of those models have no problem at all with respect to underprediction of any of the time series of observations. Both of them have problems in terms of overprediction. And these are both the same model structure. This is actually top model applied to the Brew catchment in the HIREX experiment in the UK, version of dynamic top model. But you can see that even though this is the same model structure, with different parameter sets, you're getting quite different responses. You can see here. You can see the peaks in this one that are suppressed in the other one. You can also see that this one has excursions, and this one too, outside my limits of acceptability. So that's a good reason whereby I could reject both of those models. And in fact, those were the 2 of the best ones we found. So in that case, rejecting all of the models, unless I want to say, okay, by analogy with statistical theory, I will only aim to satisfy the limits of acceptability to 90 or 95%. Unfortunately, as you can see for this one, my excursions are all associated with particular points of time which are probably the peaks of the hydrograph that I'm interested in. The 5% that I might allow myself might actually be the points that I'm most interested in trying to reproduce. So we have to be careful about doing these types of evaluation. Another example I wanted to use was in flood risk mapping, where now we have a distributed type of prediction, so a spatial prediction. And this is for an example in Mexborough in Yorkshire, a flood in 2007. And we were trying to calibrate a hydraulic model of this flood based on some post-flood surveys of depths of inundation or maximum depths of inundation after that flood. There's multiple sources of uncertainty in trying to do that, and this is a prime case where all of those sources of uncertainty also interact. Whether you've got your upstream discharge correct interacts with whether you're got your conveyance estimates correct, and how you handle things like the floodplain infrastructure for bridges and embankments and so on and so forth. So all of these sources of uncertainty interact. But you can run multiple models. You can evaluate those that give you predictions within the limits of acceptability for your observational points, and then you can use that ensemble of models to predict what you might have in terms of probabilities of inundation for, say, the 1 in 100 year, the annual exceedance 1% type of event. And that's what's been done here, and we've produced a tool that overlays those predictions on Google Earth. And of course, you can expect what happens next. You present this type of tool to local people, and the first thing they do using Google Earth is to zoom right down in on their house. The problem then is that although it looks quite nice at this scale, this is a distributed model with discrete elements. And when you zoom right down in, you can see the actual nature of those grid squares coming out into the visualization, which gives you some idea of the limitations of trying to do this even for this type of spatial type of problem. How am I doing for time, Jeff? Oh, okay. Okay. So I wanted to say something about how now you take some of those uncertainty estimates and build them into the decision-making process. Communication of what the meaning of the uncertainties is quite an important component of that. And we've written a paper with Hazel Faulkner in Ambio in 2007 that tries to address this problem, or gives a good summary of the background to that problem. And since then, we've been thinking about how to do that in practice. And one of the ideas that we've come up with is to think about this in terms of what I call condition trees, that you step through an analysis, in this case it's for that flood risk case, looking at all the decisions you've got to make about how to specify parameters, how to do your conditioning, specify your likelihoods, and so on. And there's lots of different stages, as you can see in that. Something like 17 when you add them all up, I think, were the number of different types of assumptions and decisions that have got to be made. And these are all conditions of the analysis, hence the idea of the condition tree. You can break those down, for example, for just one of them, for estimating your design flood. For example, do you have gauge data available? Yes or no. If you have data available, in the UK, we have a flood estimation handbook that has software associated with it. That's the standard thing to do, so are you going to choose to do the standard thing, and so on. You can work through these trees, and ideally you would work through them with the people, for example, from the Environment Agency, who are actually going to be users of the outcome. So they can be involved as a communication tool. This acts as a communication tool for getting their input to what types of assumptions are acceptable, what types of assumptions they might question, and so on and so forth. This is a standard analysis for the uncertainty in the design flood at that particular location. And in doing that, I think it's actually going to change the way in which we do modeling. We are going to have tools like that flood visualization map, that flood risk hazard visualization map. It also exists for the Danish water resources model, for example, where those results from modeling outcomes are presented to local stakeholders in a way that is very easily for them, for example, to zoom in to where they're most interested, to where they have their greatest knowledge, and then they will tell you where you're wrong. They will have their own limits of acceptability for how well you're doing in terms of performance, and they will be only too happy to tell the modeler where the modeler is wrong. And of course, if you're an institution, whether it's the Environment Agency or the Danish National Water Resources people or Environment Canada, and you've been producing some of these results, you will have to respond to that as an institution. And I think that's going to be a real driver in the way we do testing of models into the future and improvement of models and of data into the future. And again, there's a paper on that. Jeff mentioned the book, where you can find out much more detail about these different techniques, including a discussion of the statistical approaches as well as the group approaches. I do run the PhD course at Uppsala every year, and there's already getting bookings for next year if anybody wants to come over to do that course. And there's my summary again. Thank you very much.
Okay, thank you very much, Keith. We're just on 5 o'clock. We do have time for a couple of questions, I think. Students in the class, promised I would give you the first opportunity to ask one or two. And I'm willing to wait an uncomfortable amount of time for a hand to go up by a student. I know who you are. Okay, there will be scolding next week. Other questions? Yep, son.
So I did my master back to UK at the time that Howard was my supervisor. And at the time, my project was about climate change and how it affect one-off generation. And then the first thing Howard asked me, do you know anything about uncertainty? I say, I don't know. And then the first thing he say, of course, looking at his book, and the other book is your Wing for One-Off model prior about the GIWS. So GIWS definitely have a lot of the influence of how I approach the uncertainty. So my question is, now I came to Canada and I work with Carl on a look at the uncertainty of the river ice and see how that can probably use GIWS. And then we got 100 simulation, 1,000 simulation of the ice cover and so on. And then at the end of the day, we just say that we use the top 100 and find a confident band or a credible band. But for us, we just want to ask why I decide to take this 100 or something like that, because if I take 200, my band will be bigger, and 100 look nicer, and if I take 5, it's horrible. So that at the end, I take 100. Mm-hmm. So the question is, seems to be that use GIWS, although we can get some understanding, but we can be very subjective as well. So how can we decide that, how we decide the uncertainty bound for our simulation and so on?
That is precisely why I've moved to that type of limits of acceptability approach of trying to set up some limits prior to running the model. Mm-hmm. Okay, so, and that also allows for the fact that even your best models might not necessarily be fit for purpose. So you've taken the best 100 in some way, but there may be an issue about whether the top 1 is actually fit for the purpose that you want it to be. If we only evaluate what we've got, and this is exactly the same for statistical estimation, because you always estimate a likelihood, you always have a maximum likelihood model and what happens around that. So there's still an issue about whether that's fit for purpose. So one way of handling that is to try and set up your limits prior to running the model, and then be really strict about whether 100 or 200 or 0 actually fit within those limits, having made proper allowance for input error and so on and so forth. That means you're trying to make that assessment independent of the model itself. So that's why we've moved to that type of strategy. But there's still some issues to be resolved with that, particularly how input error should affect your limits of acceptability. That's still not a properly resolved problem, because it's very difficult to specify models of input error. That's something we're still thinking about.
Yeah. Okay,
but
thank you.
Yes, as far as possible, make your criteria independent of making the model runs.
Okay, cool.
Keith, you didn't mention types of data in terms of the power of data for model rejection. It seems that non-redundant information is important. You've talked about this a bit in the past.
Yep.
But for instance, the power of, say, isotope information for perhaps rejecting a model structure based on its inability to capture some aspect of flow source or flow pathway.
Yep.
Can you comment on that?
Yes, it lies within this hypothesis testing framework in the sense that if you've decided that you've got a set of behavioral models with respect to discharge, for example, you're still not quite sure whether you're getting the right result for the right reason. And if you have additional data that you've either collected or can collect to say whether you are getting the right sort of representation of processes, then obviously that's a way of testing those models in that context. I think there's another two issues there. One is, you mentioned isotope data, as to whether you need to introduce additional parameters to make use of that data, which may be well the case because of the difference between celerities and velocities. You may need additional storage characteristics for the processing of resonance times relative to the hydrograph responses. So that's one issue, and the other one was, I wonder. The other one was, there is, not to my knowledge, any indication in the literature about the value of data for different types of data for that type of evaluation. And that's a whole new area to explore in terms of, particularly in terms of cost efficiency for model testing. Where should we put the investment in measurement techniques or in developing new measurement techniques that will be most helpful to us in trying to decide whether we're getting the right result for the right reasons.
Right, yeah. Yes, last question by Howard.
Keith, it's great to have you here. Thanks very much for coming. We haven't this evening got into the discussion about physics-based models. And you've been involved over many decades in a discussion about the value of physically based models. So maybe just a simple question. Is there such a thing as a physically based model in hydrology?
Well, in 1989, in the Changing Ideas paper, I suggest that all distributed models were lumped conceptual models in one sense or another. So no, I don't think there is, really. One of the things I've been arguing about or against quite strongly for some time is the use of the Darcy-Richards equation in physically based models, when we know that very often through unsaturated soils you've got preferential flow pathways of one type or another that absolutely cannot be represented by the Richards equation at the scales at which we're trying to apply it. So, and that was the basis of the criticism in 1989 as well. So I've been saying that for how many years now? 20 something years, and nobody's listened really. But I shall continue saying it, and hopefully things will improve into the future. I think we could have better physically based models, but they won't be based on partial differential equations because that's not how things work. We don't have distinct gradient terms apart from those associated with gravity, but in terms of other potential terms, to make the partial differential equation approach useful, I think. So I'm much more amenable to an approach that's based on a type of representative elementary watershed type of approach. But the people who are doing that have not yet sorted out how to get the celerity velocity issue resolved to get the flux closures right for the elements with which they define their volume accounting, their storage accounting. But I think that that's definitely an area where improvements could be made and where we could make more realistic representations of what goes on in a useful calculation unit, because we have to work at quite large scales for, well, particularly if you're in the prairies or the Saskatchewan River, or there's no way you can get down with to 1 meter scale type of approaches. So we've got to make some integration, but the essence of that REW approach is that we shouldn't take small scale theory and multiply up. We should be taking into account of the scale dependence that we expect to see for the calculation unit sizes that we would use. And again, that's the difference between celerity and velocity that should bring that out and introduce hysteresis into the representations of that scale.
Okay, before I thank Keith, I want to remind you that next week we have Larry Band from University of North Carolina, Chapel Hill. We'll be back to the regular Wednesday time slot, and we'll stay that way through the rest of the term. And for students in class, we're going to have a huddle at the end of class where I'll administer the beating, and then we'll talk about the reading for next week as well. So just gather after class if you could. And again, Keith, thanks for a really provocative talk.
You're welcome. Glad to be here.